Now let's do the graph of y equals quantity x minus 1 squared. And let me put a purple circle around this to match the color of the graph, and let me put a yellow circle here to match the color of that graph. Okay, so x minus 1 squared. And I'll just go by the values we have here. We see that x minus 1 squared reaches 0 when x equals 1. So let's start just by plotting the point 1, 0. That's going to be here. And then the point 2, 1. Okay, 2, 1. Then we can go to the point 0, 1. I'll ignore the 1/2 for the moment. We'll go to 0, 1 here. And to negative 1, 4. So negative 1, we get 4. And at negative 2, we get 9. So that's going to put the graph up about here. Okay, so here are our points. It looks like we have something of the pretty much the same shape as our green graph, but shifted over 1 unit to the right. Now we can look at our 1/2 point, which gives us y coordinate of 1/4. So at 1/2, we get 1/4. And I could put that point in there. We see where it's going to be. It's going to be about here. So the graph's going to come down and kind of flatten out, come back up. And there's another point that we could graph, but we actually have enough here that we can see pretty much how the graph is going to behave. And of course we could go out to x equals 3 and get another point. We put in 3 for x. We get 3 minus 2 squared, which would be 4. So that would put us here. So our purple graph does really appear to mimic our green graph, except it's shifted 1 unit to the right. So it appears that subtracting 1 from x shifts our graph 1 unit to the right. Now you would think that subtracting 1 would shift the graph to the left, but that's not the case. We'll talk about why, but subtracting 1, it basically just, x has to be bigger in order to get the same value. If you're subtracting 1 from x before you square it, you got to square a bigger number to get the same y value you would if you didn't have that 1 subtracted. And that's why the graph is 1 unit to the right. We'll come back to that though. Okay, now what about y equals 2x squared? I believe we plotted that one in red, yep. Now remember, our green graph is the y equals x squared graph. Let me make that just a little more prominent, because most of our graphs are based on the x squared graph, although we do have the x cubed graph and the x squared plus 2x cubed graph that are partially based. Well, the x cubed graph isn't based on this one. And the x squared plus x cubed graph uses both this graph and the x cubed graph. Okay, well, y equals 2x squared. Okay, here's y equals x squared. What's going to happen if we do 2x squared? Well, that means that for every x value, we're getting a y value. So for this x value, we get this y value. Now we know that's negative 2 and this is 4, but we don't have to worry about that. Let's just look at the graph. Okay, so we have an x value, we get a y value. Now if we're graphing y equals, and that's on the graph of y equals x squared. If we're graphing y equals 2x squared, that y value is going to have to double. So we're going to get a point up here. Get a little carried away with that point. Okay, any other y value is going to double. So if we did a y value corresponding to this x value here, we would get this y value on the x squared graph. On the 2x squared graph, we would get a y value twice as high as that one. Give us a point about here. We could do that with any point on this graph. How far is it from the x-axis? Double it, and that gives us a point on the graph of y equals 2x squared. So any point on the y equals x squared graph, we double the y coordinate, staying at the same x values. In other words, we just move vertically from that point, and we get a graph on a point on the graph of y equals 2x squared. Okay, well, if x equals -1, y equals 1, so y equals 2x squared is going to equal 2. If x is 0, then y is also 0 on this graph, so we've got a point right here at the origin. Many of these graphs are going through the origin. At x equals 1, the y value on the y equals x squared graph, the green graph, is 1. We double that, we get 2, so we get a point up here. And when x equals 2, we get a point here, we double that, and we're all the way up here, right on top of this point, although I'm offsetting the points a little bit, so that our graph of y equals 2x squared looks like this. And notice kind of how that graph seems to cross the x cubed graph right about here. Now the x cubed graph is going to be higher than the 2x squared graph for every point after this. Okay, and finally we want to do the y equals x squared plus 2 graph. And what did we do here? We added 2 to every y value. If we add 2 to every y value on the green graph, if we just raise every point 2 units, then we have the graph of y equals x squared plus 2. So this point would raise 2 units to here. This point would raise 2 units, which would put it here. The origin would raise 2 units, putting it here. This point on the graph, the x equals 1 point, would raise 2 units, putting it here. Now I'm not doing this with great precision, but the x equals 2 graph, which is here, would raise 2 units, putting it here. And our graph would then look like this. Now let's note that we have our green graph, that's our y equals x squared graph, our purple graph, which is our y equals x minus 1 quantity squared, and our blue graph, which is y equals x squared plus 2. Those graphs all appear to have the same shape. It's just that one is shifted 1 unit to the right, another shifted 2 units up from the basic y equals x squared graph. Our y equals 2x squared graph, the red graph, appears to be a whole lot like the y equals x squared graph, except it's stretched out twice as high. And the y equals x cubed graph, of course, has its characteristics. All these other graphs have an axis of symmetry. The x squared graph is symmetric with the y-axis. It's mirror image. On one side of the y-axis, what you have, if you reflect it across the axis, you have the same thing on the other side. Same thing with the blue graph, the graph of y equals x squared plus 2. It's symmetric with respect to the y-axis. And so is the y equals 2x squared graph. Now the y equals x cubed graph isn't symmetric. It has a type of symmetry, but it's not symmetric with the y-axis. What you have over here is not the reflection of what you have over here. You would actually take the x cubed curve here and kind of rotate it around the origin so it's upside down, and then this would be a copy of this, but there's a rotation involved. And it has what we call symmetry with respect to the origin, and we'll see what that is. And the only graph that then the x squared plus x cubed graph doesn't really have any significant symmetry. The yellow graph goes up here, comes back down here, and goes way up here. The purple graph isn't symmetric with respect to the y-axis, but it is symmetric with the line x equals 1. The vertical line through x equals 1 cuts this graph in half in a way that the right half is symmetric with the left half. Those are all important properties of graphs. And we're going to expand on those properties, first in terms of these functions, and then in terms of some other rules.